All right, here we are, chapter 12. I don't know if it's good news or bad news, but chapter 12 is the last chapter that we will go through in the book. So, pretty exciting. Hope you've had a good year. We've definitely done a lot of algebra, no doubt. This is a nice chapter, in my opinion. I like it. It's a lot of patterns of numbers. The title of the chapter is Sequence and Series. There are 5 sections, and we are doing section 1 today in the video. And the title of the section is Define and Use Sequences and Series. So a bunch of vocab, and please don't be intimidated by this. I think I will use these words often, and by the end of the chapter, you'll know them all. You're welcome to copy them down or just listen. Sequence. So sequence is a function whose domain, all the x values, is a set of consecutive integers. Again, integers are counting numbers, also positive and negative, but -2, -3, 1, 0, all integers. So terms are the values in the range. The range, again, is all the y values of a sequence. The series, so both words start with an S, so it can get a little confusing, but the series is the expression that results when the terms of a sequence are added together. So you could have, I'm going to make up a simple sequence right now just for 4, 6, 8, 10. So I stop there. Those are 4 terms that make up my sequence of numbers. If I wanted to find the series of this sequence, I would add them up. And I should get 28. So if you add up the sequence, the terms, you get a series. Summation, because of all this adding we do, we have this summation notation, and the most common one is we have this big sigma notation. Sigma stands for sum, for the summation of a series, and we'll get into that as well. So again, basically the whole chapter vocab-wise is put on this page, and we should get into certain problems. So here's a sequence. A sequence is a function whose domain is set by consecutive integers. Consecutive meaning one after another. If the domain is not specified, it's understood that the domain starts at 1. And the values of the range are called the terms of the sequence. So the domain would, 1, 2, 3, 4, again, integers, consecutive, going to some value n, could go to 5, could go to 100, could go to 1,000, whatever. And the range then, and this is neat notation, this is a sub 1, this is subscript, again, notation, and these would be the answers. So the difference between a finite sequence and an infinite sequence is a finite has an end to it. Oh, it's almost like the one I made up in the problem before, but this 2, 4, 6. And then it's over. You have 4 terms in your sequence. An infinite sequence, by putting the ... and you realizing the pattern, like right away, right? I don't have to tell you what the next term is. It's 10. And the next one, 12. The next one, 14. And you could go on forever. The ... turns this into an infinite sequence that goes on forever. A sequence can be specified by an equation, or, if you don't want to use the word equation, you could say it's a rule. For example, both sequences above are described by the rule 2n, right? So n would be 1, n would be 1, 2 times 1 is 2, n would change to 2, 2 times 2 is 4, and n changes to 3, 2 times 3 is 6, and so on. So again, we keep putting, these domain numbers, 1, 2, consecutive integers into the rule, and into the rule means here, into the rule. So 1 would go in, 2 would go in, and then we would get the terms, 2, 4, 6, 8. And these guys could be labeled as a sub 1 is 2, and a sub 2 is 4. So there's a labeling system, and it's a good one. A sub 3 is the third term, and the third term is 6. And again, there's a rule or an equation that we could use. So here is a rule. The rule says take n, and again, because n isn't specified, we are going to plug in values 1, consecutive integers 2, 3, 4, and so on. And we would plug them here in for n. So let's kind of look through it. So the first term, right, we would set n equal to 1. We would put 1 in for n, and then we would calculate. So this should be 1 plus 1 is 2. 2 to the 2 is 4. I have my first term. Let's do the second term. So now we set n equal to 2. We then substitute in 2 for n. 2 plus 1 is 3. 2 to the 3 is 8. And that is the second term. Third term. Fourth term. I think we keep going. Fifth term. And you can see, again, these 3's, this is n changing and increasing every time by an integer. And the answers, or what we say are the terms, are 4, 8, 16, 32, 64. Can you guess the next one? 128. Can you guess the... Oh, they didn't do the next one. We can do it for them. 256, right? So you should, there's two ways to follow the rule. You're like, hey, wait, you didn't even use the rule here, man. But yeah, but I can start seeing this pattern existing. And that's kind of, to me, what makes this chapter, I don't know, fun and interesting is all the number patterns. So, last example, we were given the rule, right? And now this example, we're asked to make up a rule. And this can get really, some of these rules can get really hard. So you're kind of looking, can you see what pattern, how are these numbers changing like this? There's a 1, there's a 4, a 9, a 16. And there's really nothing I can do to help you other than, to encourage you to kind of see if there's a pattern. Am I adding a number, multiplying, squaring, subtracting, all the different operations that you have? Hopefully you're kind of recognizing this looks like, the perfect squares, right? The next one I think would be 25. So we can look right away and see, and you can see, yeah, it was. The terms are basically plug in 1 and square it, and you get the first one. Plug 2 in and square it. And again, realize you should be figuring out the pattern where n is changing, is going from 1 to 2 to 3. That's a big part of the pattern recognition. And so finally, the way we write the rule is right here. We would write, and you need to be able to do this, right? So you need to not only figure out the rule, but know how to present it, meaning a sub n, and again, this is just notation. This is saying all the terms, n going from 1 to 2 to 3 to 4 to dot, 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 could go on forever. And we're squaring it, so it n squared. Whew, next one. Tricky, right? So 0 to 7 to 26 to 64. So I gotta admit, I already looked ahead, so I have an idea what this, I know what it is, but it would be hard to recognize this, right? The pattern here is basically you're cubing n and subtracting 1 away from it. So this, imagine if this was 1, 8, 27, 64, 125, and then you might recognize that I'm taking the integer 1, 2, 3, 4, 5, and I'm cubing them. But then how do I drop to 7? How do I drop to 26? How do I drop to 64? I'd have to then subtract the number, subtract the 1. Whew. And so you can see that that is the rule in this case, right? And the rule, again, all that, there's a lot of nice written things to help you get to the rule, but make sure you appreciate this is the answer. You would have to present it accordingly and correctly with the notation. A sub n is equal to n raised to the power 3 minus 1. And you could just sit here forever and keep plugging in the next integer. So I went up to 5. Hey, you want to take it? 6 raised to the power 3 minus 1. That's the next term. 7 raised to the power 3 minus 1. That's the next term. Hey, see if you can't do these two problems. Hit pause. When you're ready, hit play, and I will present the answers. And there they are. So pretty straightforward for problem 1. You just plugged in values of n. n is 1, so you get 3 minus 7, negative 4. n is 2, 6 minus 7, negative 1. n is 3, 9 minus 7 is 2, and so on, and so on, and so on. Fun, right? Should be fun. Notice the function notation. This time they said f of n. Whoa, zoomed it in. You could have also written a sub n, or actually they presented it. I take it back. Here you have to write the equation. So again, tricky when you see a sequence that toggles negative, positive, negative, positive. There's something going on with the squaring, right? The only way to do that is to, when n is raised to an odd power, you'll get an odd answer. You raise n to an even integer, 2, 4, 6, 8, you'll get all your answers coming out positive. So when you see that toggling, realize that there has to be that. The only way to do that is by raising. And then notice the pattern of 3, 9, 27, and 81. Hopefully again. And we'll practice these. These are, they can be quite difficult. We'll try to keep it on the easier side. So here we go. We're switching now to the series. And again, notice how the series is presented, right? A sequence, here in this answer, commas. So I'm just listing you the next terms. But in a series, we're going to add up the terms. We can have a finite series where there's an end to it, right? And my total here looks like it would be 20. There's an answer, 20. But there's no way to actually answer this question, right? It goes to infinity. I mean, it's just going to balloon up, blow up. Let me read you the top here. I skipped that. When the terms of a sequence are added together, the result expression is a series. A series can be finite or infinite. We can use summation notation to write a series. So this is powerful. And I really like this notation, and you're going to get a lot of it. So I hope you like it too. But here the rule is 2 times the n. And again, now with summation notation, we typically use the letter I. I don't know why, and I don't think there's anything wrong if you write n there, but just to be, kind of up and up with how most of the math world does it, they'd use an I. So the rule is 2 to the I. I is going to go from 1 to 4. Pretty cool. So again, you have to learn this system. Definitely on your note card is a good one. But you can see here, this would, if you got this system, you would say, oh, that's 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. Right? So you're toggling, or you're including the numbers 1 through 4 as integers, and then you would calculate, oh, that's a 2, that's 4, that's 6, that's 8, and then I'd add them up. So this one, notice how I get the dot, dot, dot. I use the infinity symbol, and it goes forever. Yep, I did everything there. So here they're saying, can you write the series that's given to you in summation notation? Notice how they dot, dot, dotted it and then ended here. So this is going to be a finite series, and we have to try to figure out the rule and figure out where it's going from n or I, from I to 1 equal to 1 up to I equal to, and we're not quite sure yet, and that's going to make this a little bit trickier. Notice that the first term, is 3 times I plus 1. The second term is 3 times 2 plus 1. I didn't really recognize that, but thanks for telling us the rules. Again, tricky to come up with these rules. Here is the rule, and it looks like to get this to go to 5, this would be 3 times 15, which is 45. So I is 15. And I have to admit, like making this problem easy by showing you the answers, but this would be a tricky problem, for all of us to figure out. First you got to figure out the rule, then you have to figure out how high they're going, and then you would write it in this, and this is the final answer. So it's the rule, right? 3 times some integer. So 3 times 2 with 6, add 1 is 7. So it's the second term. We're going from 1 up to 15. The second one, because it's dot, 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 we can just say it's going to go up to infinity. So I kind of like those infinite series. What's the rule look like? Looks like 2 here, raised power 3, all over 1 over 3 raised power. Yeah, so I think the rule is pretty easy on this one. I got that one. Is 1 over I to the third, and then I'm going from 1 to infinity. Sorry, that is an I. I wish they made a little tail. I like our eyes to look like that. Over 1 with your series from I equal to 1 up to infinity. Nice. See if you can do these two. Again, try your best. Definitely get in that, write that summation notation. Nice Greek letter, right? Big Greek letter. You can write as big as you want, and then the rule. Then you should use I in your rule, and then this goes from I